Okay, we are in the AP style review of applications of differentiation. If you can find that packet.
You know, if you want to. Dalton's is on the board.
Yeah, you can have Dalton's cup if you want. It's on the board.
Like, Dalton, if you're watching this, you'll get 100% if you tell us a subject.
Okay.
Over.
The packet even looks bigger.
Yeah, it looks huge.
Okay, so we're doing some multiple choice problems. These are gonna feel like a while ago, like these are kind of like chapter 3 problems that we did, but you know what? We're always reviewing, right? It's good. Good stuff. Reviewing for the exam. So, this one would be on the no calculator part. And we're given a polynomial function, and they want to know where we have a point of inflection. So what do we have to find for point of inflection?
The second derivative.
You betcha. Second derivative changes sign. Okay. So nice, easy polynomial. First derivative, 15x to the 4th plus 40x cubed. Second derivative, 60x cubed plus 120x squared. So I'm going to create a signs chart. But first I got to find like the critical points here. Set it equal to 0. Remember how to find derivatives? We've been doing so much integration. Hopefully we didn't forget derivatives.
Can we just divide by 60x squared?
Yes. Yes, you can. Well, you can divide by 60, but the x squared you technically have to factor out. I wrote it like this. But you could divide off the 60 if you want. Just don't forget that x squared is going to give us a critical point of 0 and -2. Okay. So I'm looking for where the second derivative changes sign, and I do not have a calculator. So remember what I showed you to do is to like look at like the factored form like this of the second derivative. This is why I don't divide off anything, just in case like I keep it like in this factored form. So when we do a test like -3, this is always going to come out positive. Obviously, you have 60 times -3 squared. That's always going to come out. You don't even have to do the numbers. You're going to have a positive times -3 plus 2 is going to be a negative. So now it's going to be negative to the left. Don't waste your time like actually trying to find the numbers. All we care about is the sign. Okay, so then if I do like -1, which would be in between -2 and 0, again here, it being squared is going to be positive. And now -1 plus 2, that's also going to be positive, positive times positive, positive. All right, and then one more to the right, probably test 1. Another positive, positive. So my only point of inflection is actually at -2 because the second derivative has to change sign. That's saying it's changing concavity. So I don't really know if it's like increasing or decreasing. I'd have to do like the first derivatives test. I know it's concave down, like a frown here, and this is concave up, concave up. So there must be concave up, something like that, where second derivative is 0, but it doesn't change concavity. Okay, not bad. Ooh, this one's fun. Oh gosh, you guys, we're going to get to do a full FRQ today. That's exciting stuff.
How many FRQs are on the 50 test?
6.
And there's what, 60 multiple choice? Or 48?
45, I think. I think it's 30 no calculator, 15 not. 30 no calculator, 15 with your calculator, I think. I gotta double check that number. But the numbers are weird. Like they jump like 1 to 30 or the no calculator, and then it jumps to like 75 to like 90 or something because you fill out the Scantron that way. So that's why like some of these numbers are kind of weird. All right, this one will be another no calculator. Let f be the function defined by this cubic polynomial on which of the following intervals is the graph of f both decreasing and concave up. So we know our graph is decreasing when the derivative, the first derivative, is negative. And we know it's concave up when the second derivative is positive. So same idea of finding like the critical points here, and then we'll make one big sign chart and kind of compare the first and second derivative and see if there are any intervals where this happens, where the first derivative is negative but the second derivative is positive. Okay, so first derivative, nice easy polynomial. Set it equal to 0. I would divide everything. Sorry, this should be 3 times 2 is 6. Good catch. Okay, I would divide everything by 6 to make this easier to factor. And remember, on multiple choice, our work is not graded, so we don't need to show every single step. We need to work quickly but accurately. Okay, so for our first derivative test, we have critical points at 2 and -1. Now I'm going to go ahead and find my second derivative while I'm doing my algebra here. 12x minus 6, and figure out where that's going to be equal to 0. That would be at 1/2. Okay. So I would do one big sign chart and put everything on here. That's how I like to do these. So -1 and 2 are for my first derivative, and then 1/2 for my second derivative. So I'll test these in the first derivative, second derivative. Okay, first derivative. Again, I'd put it in this like factored. So -2 minus 2, we're going to get a negative times a negative. Negative times a negative, so that's going to be positive. Okay, quickly test 0. 0 minus 2, 0 plus 1, that's going to be a negative times a positive, that's negative. So everything in between -1 and 2 is going to be negative. And then when I tested 3, 3 minus 2 is positive, 3 plus 1 positive, positive. That's what our first derivative is doing. I know I said this, but again, just pay attention to the sign. Second derivative, really easy. Plug in something to the left of 1/2. 0 minus 6, that's going to be negative. Something bigger than 1/2, such as 1. 12 minus 6, that's going to be positive, everything to the right. So this is essentially like testing my second derivative. This right here is essentially my first derivative. Okay, so do we have an interval where my second derivative is positive and my first derivative is negative? You betcha, right here. From 1/2 to 2. D. Ooh, a little particle motion coming up next. Okay. Last multiple choice one for today. A particle moves on the x-axis so that at any time in between 0 and 1 second, its position is given by this position function with sign involved here. For what value of t is the particle at rest? Okay, do you guys remember how to find when the particle's at rest?
Velocity 0.
Good, yeah, when the velocity is 0. Perfect. And we know the velocity is the derivative of the position. So here we have derivative of sine of cosine, 2 pi t, don't forget chain rule, times the derivative of the inside would be 2 pi, plus the derivative of 2 pi t would just be 2 pi. This is another, no calculator, just so you know. We gotta be able to solve this with no calculator. Okay, so just like Mark said, we want to know when this is 0. So I'm going to bring this 2 pi in front here. Ooh, we're going to start solving trig equations in pre-calc next week. See if you guys remember how to do this. So I would probably, you could factor out the 2 pi if you want to, or I moved over this 2 pi. And I did this. And I divided both sides by 2 pi. So I got to here. And they do give us, we only want the values like in between 0 and 1 for t. So then I basically asked myself, like, at what angles do we have a cosine value of -1? So that's here, when cosine is -1. That's at values of pi, or multiples like of, I don't want to say multiples of pi, because 2 pi is technically a multiple of pi. Odd multiples of pi. So I want to figure out when this would be pi. Or another way you could do that, guys, another way you could like algebraically solve this, I guess I'm not quite sure how you learned how to solve the trig equations. Sometimes they're different. You could take like the inverse cosine of both sides. I don't know if this looks familiar to you. Because the inverse cosine of -1 is pi. And this like gets rid of taking the cosine. So you get to the same spot. That's kind of how you like algebraically do it. Do either of those feel familiar?
I'd say the inverse.
The inverse, this way. Looks more familiar. Okay. So we can easily solve this then for t. Either of these. We get 1/2. Which was in that interval in between 0 and 1. D. B, D, D.
It's like one of your tests.
No, I'm just trying to prep you for the exam.
A, C, E,
And I think I've told you this a couple times, but this changed in 2010. That now there's only options A through D. This is just from an old exam, but you guys will only have 4 options. You won't have E. But sometimes on my test I put 4. Sometimes I put 5. Depends where I get the problem from. Or how many silly solutions I can come up with. Okay, let's try some FRQs. Okay. I don't remember which exam this one's from. So we are basically given this table here that gives us different outputs for 2 different functions, f and g. F and g are twice differentiable functions. Anytime they tell you that, if it's differentiable, we know it's continuous. Differentially applies continuity. So if we're ever asked, we actually are going to do one. If we're asked for like a mean value theorem or an extreme value theorem, a lot of the criteria and the hypothesis that we have to meet is that it's continuous. Anytime you see it's differentiable, that's good. That means it's going to be obviously differentiable and continuous. So values of like their actual outputs and their first derivatives are given for different values of x in the table above. Okay, so just to walk you through this is basically saying like here's all my x values and some intervals. And my f of x, my output values are positive, and my first derivative has these slopes at these points and with a sign on the derivative. It's kind of how you would read that. Okay, so part A says, find the x-coordinate of each relative min of f on the interval -2 to 3. So remember, a relative min on the actual graph would look like this, or it's where f prime changes from, our graph changes from decreasing to increasing. So our f prime changes from negative to positive is what we're looking for. There is one spot that happens on f. The first derivative changes from negative, hits a 0, to positive. So x equals 1 is a relative. Sorry, was I saying max? Did I say min? Relative min. Justify your answer. Because f prime of x changes sign from a negative to positive. And you want to use like the derivative in your justification there. Okay, that wasn't too bad. I wonder how many points that was with. Probably 2. Oh my gosh, we could probably do now C and D. I don't know if we could be ready for D, but now that we know natural log. Okay, sorry, we'll stick with just B. Explain why there must be a value C in between -1 such that the second derivative equals 0. Okay, anytime you're asked to like explain or prove why a value exists, that's usually a hint at one of the big 3 theorems that we're going to use. So the hint that it's the mean value theorem is when you see like a derivative equals something. Now, this one has a second derivative, so we are actually going to use like the mean value theorem with the first derivative applied to the second derivative. Okay, so let's see what that means here. Let me zoom out a little bit. It's going to take up a lot of space. Not that. Not that. Here we go. Okay. So basically, when you say something like this, that's usually hinting at the mean value theorem where they're telling you like, explain why over an interval we have an instantaneous rate of change equal to this. Because the mean value theorem is this right here. That the average rate of change over an interval is equal to the instantaneous rate of change of some value in that interval. Now, I see here that they want me to apply this to the second derivative, so you can actually do this with using the rate of change of the first derivative. There has to be an instantaneous rate of change in that interval for the second derivative. Like you can apply it at that level too if you're comparing first derivative to second derivative. I don't know if we've done one like that before. Okay. Now first, for mean value theorem, there's 2 things you have to prove in the hypothesis, 2 criteria you have to meet, and that it's continuous on the interval, on the closed interval, and differentiable on the open interval. So this is what I was saying before. They want us to use f here. They're telling us that this is a differentiable function, both f and g are. So what all you need to say is, since f is differentiable for all real numbers, f is continuous on the closed interval, -1 to 1, and differentiable on the open interval, -1 to 1. That's all you need to state, those 2 things, in order to use the mean value theorem. I have like this big cheat sheet of all the 3 big theorems that we'll look at as we're reviewing for the AP exam. Therefore, by the mean value theorem, or you could say, oops, I spelled that wrong. The mean value theorem guarantees there exists at least one x equals c such that the average rate of change over that interval is equal to the instantaneous rate of change somewhere within that interval a to b. Okay. I believe if I scroll, it's not going to save my ink. So let me drag it up. Okay, not worth it. So, here's how we would show that then. Because they're trying to show that the instantaneous rate of change over that interval is 0. Okay, I'll just read it just real quick. So you got this. Well, I'll do the average first. Our interval is -1 to 1. So there's your A, there's your B. So you gotta find f prime of 1 minus f prime of -1 all over 1 minus -1. Okay, looking at my table, what is f prime of 1? 0. Yep. So you look up here, f prime of 1 is 0. What's f prime of -1?
0.
There you go. That is just fine. Okay, let's see how far we get on the next one, but this one I'm excited about because we can do all 3 parts with what we knew just based off of chapter 3. We'll at least get through A and B probably. Okay, particle X moves along the positive x-axis so that its position at any time greater than or equal to 0 is given by this position function. Is particle X moving toward the left or towards the right at time t equals 1? Give a reason for your answer. So since our velocity is our speed with direction, we just want to basically find my velocity at 1 and check the sign. So to find the velocity, we just find the derivative of the position, which is 15t squared minus 18t. And again, all we really want to evaluate this is at 1. So 15 minus 18 now to give us a -3. Does that tell us our particle is moving to the left or to the right? Left. Yep. Since, here's my justification, since v of 1 is negative, or you can just say less than 0, or you can write out is negative, the particle is moving to the left. At t equals 1. Okay, next part. At what time, when the time is greater than or equal to 0, is the particle farthest to the left? Justify your answer. Okay, well we know at 1, it's traveling to the left, so we need to figure out what's going on before, what's going on after. So we're gonna find some critical points here. We're gonna figure out when our velocity is 0. We'll make a sign chart. Okay, so I personally write it like this, factored. So at 0 and at 6/5, so just a little bit more than 1 second, this particle is at rest. All right, well, we already tested 1 and it was negative. So then we should test 2. So again, plug it in like this factored form. 3 times 2 is positive. 5 times 2, 10 minus 6, that's positive. That's going to be positive. All right. So what this tells us about our particle, so he starts at 0, and he's going to the left, going to the left, going to the left, and then he stops at 6/5 just for an instant, and then he travels to the right. So when would he be the furthest to the left? At 6/5, right? Right here. Because then from then on, he's going to the right. Okay, so I'm going to write my answer up here. So I would say the particle is farthest to the left at t equals 6/5 because velocity is negative for everything in between 0 and 6/5. And my velocity is positive for everything greater than 6/5. So again, folks, like you can write that out like in words too. That's fine to justify your answer, but also it would save you time to like instead of writing my velocity is negative, like use math symbols, say it's less than 0. The next problem is really intense and we only have a minute, so I'm not going to start it. I'll just have to remember we gotta do one more. I feel like the next one, the rate of change of the area, I feel like it's kind of like a little related group type of one. Oh, it's not too bad actually. Okay, we'll stop there. Riley, do you have some stuff done?
Yeah.